Hello, Flat Earth researchers, debaters and debunkers. One of the first things anyone looking into Flat Earth will do is reverse engineer the heliocentric model and the globe Earth idea that goes with it, especially when it comes to one of the fundamental assumptions that we live on a globe, and that is the transition between day and night. And of course, in a heliocentric model where you have the sun at the center and the Earth orbiting the sun, if it were a flat Earth in this scenario, then of course you wouldn't have day and night. You'd have day constantly on one side and night constantly on the other side. So the only way around this to have a smooth transition is do what Copernicus did and assume that the globe, or the Earth, is another planet, making it a globe. And then, voila, you have a way to transition between day and night by spinning that globe as it orbits the sun. Now, this is just a model, the Copernican heliocentric model that assumed many things, such as the distance and size of the sun and the Earth being a sphere and rotating, among other planets. So what we'll do in this particular video is look at a fairly straightforward analysis. This was given to me by one of Phuket Word's patrons, Bruce Stevens, and so he's knocked up this assessment here of how we could consider the different positions of the Earth in relation to the sun, or the sun in different positions, and think about what would really make a difference to the length of a day and night in any given location on the Earth. Now, of course, it's understood that in most places on the Earth, the length of a day changes throughout the year. Short days in the winter, long nights, and longer days in the summer. And we have the equinox, where you've got about 12 hours of each. But Bruce makes some excellent points in this, and we're going to have a look at, first of all, what NASA says is the answer to the speed of Earth's rotation. You can go and check this yourself, but basically it says that at the equator, the circumference of the Earth is 40,070 kilometers, and the day is 24 hours long. So the speed then is 1,670 kilometers per hour, or 1,037 miles per hour. So straight off the bat, you've got to remember, or keep in mind, that this is merely a calculation. All right, based on the assumption that the Earth has a certain circumference and it's a globe, and based on us knowing how long it takes for the combination of day and night to take place, being 24 hours, we can, of course, with that a fairly simple calculation, work out the assumed speed over a certain amount of time. All right. But this is just a calculation. It's not a measurement. The only thing you can measure really is just how long the day lasts and how long the night lasts on any given day or night. So, with that in mind, this decreases by the cosine of your latitude, so that at a latitude of 45 degrees, cosine 45 equals 0.707, and the speed is 0.707 times 1670. So that's the kilometers per hour. Okay, equals 1,180 kilometers per hour. So you can use this formula to find the speed of rotation at any latitude. All right. So again, it's something that you can model mathematically quite easily, given some assumed dimensions and latitude lines on a sphere. And so, of course, the mathematical model would appear to prove itself, and for many scientists or mathematicians, that is proof enough. The mathematical model works, so we do not need to take anything else into consideration. So let's launch now into what Bruce is pointing out here. And with a side note, NASA tells us to make sure that when you use your calculator that you set up the arguments for the trig functions in terms of degrees, not radian. Again, degrees is a very important aspect of the globe. Distances are converted into degrees and time is converted into degrees. Again, this works nicely in a globe or spherical or even two-dimensional circular model because you have 360 degrees in a circle. So this is also an aspect of the model that you must keep in mind. Physical distances are converted into angles, and the time that we use, of course, we know that you can fit 12 or 24 hours into a circle, just like a clock. So this conversion into degrees rather than radians is another aspect of why a globe is used for navigation and would appear to work, because you're working in a model that has been comprised of degrees that are conversions of distances and time, putting them into the same format, the same metric of measure or calculation, as it were. Yeah. For example, you might have inches and pounds as a weight, inches as a measure of length and pounds as a weight, and you want to marry these two together in some kind of model. Well, what you need to do is convert them into something that would work cohesively and make things a lot more simple rather than having to do conversions for every single aspect of the model. So of course there comes the metric system, for example, where you can convert inches into centimeters, and you can then convert pounds into kilograms or grams. So then you have this metric system which you can base your model on. Okay, so in this instance, again, just to emphasize that the globe and the heliocentric model is all based on converting these distances and timing into degrees. So let's go into how Bruce has analysed or the questions that are being asked here about what difference would it make where the Earth is in relation to the Sun. So Bruce says, whatever. We all know the day is broken down into 24 hours and an absolute constant speed of rotation of the ball we live on. The Earth does not speed up or slow down in its daily spinning, right? I even came across mention of the Earth slowing down its rotation by 1.7 milliseconds in the last 16,000 years. I'm all for precision in science, but sheesh. So, I don't care about the speed of rotation for this analysis, only that the ball we are looking to examine is spinning at a constant speed. For the following pages, containing illustrations, consider the effect of the light source upon the spinning ball, and how long any single point upon the spinner would be in light and darkness. So here you just keep, for your reference, we've got the light source is the sun, and the globe is the spinner. Alright, so here we have a fairly straightforward illustration of the sun in the center and the globe Earth and its orbital path around the sun. So in this first example, assuming spinner is spinning at a constant speed of 1037 miles per hour, taking 24 hours to complete an axis rotation, how many hours of light would any single point have per 24 hours? How many hours of dark would any single point upon the spinner have per 24 hours as well? Well, it's fairly simple that we should have 12 hours of light, 12 hours of dark. And the question is, does this change if the spinner's axis is tilted? It seems to me there is still a perfect 50% light-darkness terminator that is encountered equally at 12 hours due to perfect rotation speed. And this, of course, you can test yourself, shine a light on a ball, and whatever angle you have that light facing the ball, you're always going to get half of the ball, or 50% of the ball, lit up and the rest in shadow or darkness. And so the explanation we have from the globe Earth believing fraternity is that it's a question of direct and indirect sunlight. So this tilt or alleged tilt of a spherical Earth would give us light coming in directly or indirectly to certain obviously above the equator it's supposed to be quite direct all the time, but the further north or south you go from the equator, the less direct that light will be. Now this is ironic really, and it's also a contradiction in the model, because the sun is supposed to be many times larger than the Earth, so the sunlight that it is emitting should cover the entire half of the Earth, and there shouldn't be any difference in the actual intensity or of the light that's coming to the Earth, regardless of any assumed curve on that surface. It's still going to all be direct sunlight, because it's from a light source that is supposedly much larger than the tiny Earth in comparison. All right, so that's just a simple illustration of how you could imagine wherever you want to put this terminator line, you're always going to get 50% of the Earth covered, whether it's pole to pole or whichever poles you're referring to. So we'll move on to example 2. Again, assuming spinner is spinning at a constant speed of 1037 miles per hour, taking 24 hours to complete an axis rotation, 1 day, how many hours of light would any single point have per 24 hours? How many hours of dark would any single point have per 24 hours? 12 hours light, 12 hours dark. Okay, so that's again fairly straightforward. All right. In example 3, got the Earth over here. All right, so it's basically we're following the Earth's orbital rotation at different points in the year according to the heliocentric model. And in this example, we have, again, assuming spinner is spinning at a constant speed of 1037 miles per hour, taking 24 hours to complete an axis rotation. How many hours of light would any single point have per 24 hours? How many hours of dark would any single point have per 24 hours? And the answer we have here is 12 hours of light, 12 hours of dark. Example 4, okay, coming round again to close to the start point. Example 4, again assuming spinner is spinning at a constant speed of 1037 miles per hour, taking 24 hours to complete an axis rotation. How many hours of light would any single point have per 24 hours? How many hours of dark would any single point have per 24 hours? 12 hours of light, 12 hours of dark. All right. And example 5, now you can see here that the sun has been put off center, so and the Earth over here, so we're basically creating a greater distance between the Earth and the sun. Would it make any difference if we conceive it like this? In example 5, again, assuming spinner is spinning at a constant speed of 1037 miles per hour, taking 24 hours to complete an axis rotation. How many hours of light would any single point have per 24 hours? How many hours of dark would any single point have per 24 hours? 12 hours of light, 12 hours of dark. Okay. Now you can think about this, and you might be jumping to the assumption that just because you're further towards a pole, you would have a greater or lesser amount of sunlight depending on the tilt. But really, again, you're only ever going to be having, it's always going to be 50%, okay? So even if you're at the top, as it were, near the top, near the North Pole, for example, with not much space between you and the pole, and you're more tilted towards the sun, that sunlight is still going to hit half of that arc divides light and dark between those two sides, on either side of the pole, as it were. Example 7 here, we have, again, assuming spinner is spinning at a constant speed of 1037 miles per hour, taking 24 hours to complete an axis rotation. How many hours of light would any single point have per 24 hours? Here we have the Earth and the Sun very, very close together in this particular aspect, and the Sun right over here. How many hours of dark would any single point have per 24 hours? 12 hours of light, 12 hours of dark. Okay, it really doesn't make any difference, does it? Now here, Bruce has put the globe Earth way out here, maybe another few million miles away. No, let's say another 60 million miles away from where it's supposed to be. So example 8, again, assuming spinner is spinning at a constant speed of 137 miles per hour, taking 24 hours to complete an axis rotation. How many hours of light would any single point have per 24 hours? How many hours of dark would any single point have per 24 hours? And again, it's 12 hours of light, 12 hours of dark. Again, Bruce keeps emphasizing the fact that we're talking about spinning at a constant speed, and one complete axis of rotation being 24 hours as we measure the full length of a day. So essentially what you still should have in that case, based on this calculation, really, is 12 hours of light and 12 hours of dark on this rotating spherical Earth. Alright, now in example 9 here, where we've got the Earth further away again from where it's usually put, assuming the spinner with the same amount of miles per hour, 24 hours rotation. How many hours of light would any single point have per 24 hours? How many hours of dark would any single point have per 24 hours? 12 hours of light and 12 hours of dark. Again, we're talking about the rotation. The position really in relation to each other makes no odds whatsoever. Example 10, the same question, and we still have the same answers. 12 hours of light, 12 hours of dark. Okay. Now, in this example, 11, again, assuming spinner is spinning at a constant speed, taking 24 hours to complete an axis rotation, how many hours of light would any single point have per 24 hours? And how many hours of dark would any single point have per 24 hours? 12 hours of light, 12 hours of dark. Basically, the distance from the light source and location on ecliptic does not have any bearing on the day-night cycle. This is the conclusion you can reach from basically just putting the Earth in all these different locations. The day and light cycle is always going to be the same. And here Bruce has put in these different axes of rotation again. So Bruce basically concludes this with talking about the different lengths of day in Phuket, for example, which we'll have a look at. And Bruce is from Michigan, so he sees a deviation. He says, I wish I had my personal observation logs from a couple of years ago, but our length of day deviates nearly 6 hours throughout the year. I pulled numbers from the internet for New York, and they report numbers near enough to mine as I remember them. So the New York's shortest day with daylight hours is 9 hours and 15 minutes. New York's longest day with daylight hours is 15 hours and 6 minutes. So this is a change of 5.75 hours and nearly 50% of the total 12 hours light-dark, and is not accounted for by tilt of axis, nor path of ecliptic when you look at the actual physics and geometry of a light source acting upon a sphere that rotates at a constant speed. And would love for someone to model this someday. Food for thought. Yeah, it's excellent food for thought, and it's something we can look at in terms of the day length to just check those figures there. But again, keeping in mind that these are all calculations based on observations. Yes, you can observe these different times, and they are true per se, but that doesn't confirm the model. Okay, it might fit with the model, but it doesn't confirm that the model is our reality. it's again easy enough to do when you have everything in terms of degrees. So let's just have a look at this on timeanddate.com. I brought up Phuket sunrise and sunset day length. At the moment it's looking at March. You can if you've never used this before, it's quite handy. So you can see the sunrise. You go to the sun and moon calculator, or the sunset and sunrise calculator here. Okay, so in Phuket we are fairly near the equator. I think we're 7 degrees above the equator or something like that. So it's fairly consistent. Okay, so what you can do is you can just go through the year here, January, February, March. Now, what was the equinox? Is March the 21st is the equinox. So if we go around here, we can see this. All right, this line now, and what you can see there is down here we have the daylight. Okay, the hours of daylight from 6:46 in the morning. This is back in February at the moment, January 29th. We'll come back to the equinox in a second. And that total is 11.47 or 11 hours and 47 minutes of daylight. Okay, and so there are some slight changes throughout the year. We can see here, going from January, we've got 11:41. It goes up and up, and then we've got 12 hours by March the 12th. Okay, we've got 12 hours of sunlight. All right, and it goes on and up here by May the 14th, 15th, we've got 12 and a half hours. Okay, May the 18th, and it still continues to increase. All right, now it's starting to go down. So from July the 25th in Phuket, we start to see a decrease in the number of hours of daylight. Okay, but we've got not much. We've got less than an hour's difference in the total amount of daylight per day, and so you can also see on this chart down here, we've got the sunrise and sunset time. Also, you've got the heading of the sunrise and sunset, so it's almost east and west directly there. And you have the length of the day length, and you've got the difference. Okay, that you can see. So and so it goes on. Now, if we move on to Bruce's area, which is Grand Rapids in the US, you can see the map here. That's the location. So fairly high up in the North US. All right, and we can see here January. All right, this period here, you go and have a look at the daylight times, 8 o'clock in the morning until 5 or nearly 6 o'clock at night. And in January we've got about 9 hours and 50 minutes. Okay, that increases to 10, and then we have a bit of a jump here suddenly to well, it appears to be a jump, but that doesn't. 11:42. Well, it slightly jumps by a couple of minutes. Okay, and that's around the equinox time, I believe. Well, if we go to March 20th. Okay, there we go. We've got so actually on the vernal equinox in March, in this location we have 12 hours and 9 minutes of daylight. So although it's marked down as the equinox in which we are supposed to have 12 hours of daylight and 12 hours of darkness, equinox equal day and night, we actually have more, almost 10 minutes more daylight. That'd be interesting. Let's just go back and have a look at what it says for Phuket again. March the 20th. Okay, and we have 12 hours and 6 minutes. So more of about 3 more minutes of sunlight in Grand Rapids than in Phuket at that time of year. All right, and so let's just carry on with this as we go through March, April. All right, and May. We've got in May the 1st, for example, in Grand Rapids, we have 14 hours of daylight. 15 hours by June. Of course, this is the height of summer. And okay, it starts. So we've got 15:01 there. Let's just see where it gets the most. All right, now again, this is the point I wanted to point out here in June at the height of summer. If you have a look at, okay, we'll go to June the 16th and have a look down there at the daylight and total hours of daylight as these figures change. Daylight here is 6:03 in the morning until 21:23, and that's a total of 15 hours and 21 minutes. Now let's move to June the 17th. We still have 15 hours and 21 minutes, and we move to 18th and 19th. We still have 15 hours and 21 minutes. All right, and June the 20th. So something's happening here, and even if we go as we go to the 23rd, we have 15 hours and 21 minutes still. All right, so it's not until June the 27th that things start to change, and we have a slight decrease that will continue on to the winter of the number of hours of daylight. Okay, so let's just, I'm going back now. June 26, 21. Okay, just keep an eye on the total time there. And okay, we do have a slight change in the. No, we don't have any changes really in there. Maybe some slight changes in the actual beginning of daylight, the time that daylight begins. Okay, so okay, so June the 15th. So June the 16th, it's the same all the way up until June the 26th, 26th, okay, 16th to 26th. Several days, the sun isn't really giving us any more or any less daylight. It's the same amount of daylight. So what's happening at that particular point? Is this accounted for in the heliocentric model? Do we okay, this is maybe what's part of this so-called elliptical orbit where you have a bit of a pause. Okay, but again, this is a way you can illustrate things in a graph. You just get this kind of peak, and then before things start decreasing. So if you change that elliptical orbit to some kind of upright vertical graph, you would see this slow down as you reach the peak, and then things would hang for a while before they started descending. Okay, this is just again to illustrate the fact that it's a mathematical illustration or a concept that can be illustrated in terms of graphs or geometry and in many ways, as long as you're just plotting those points somehow. Yeah. All right. So as Bruce has said in this, it would be great if someone could model this someday, but I think we can all model this in our heads, and there are plenty of existing models, and in a way what we've just been looking at there are models, because this is data that can be converted into various formats. All right, so try this out yourself. It would be great to see if anyone has any comments to add or arguments to put forth, but see if you can come up with something that would either justify or just tells us that no, this certainly doesn't relate to us actually being on a ball. Again, there's no presumptions here. There is an analysis of the model that we are given, and you can see that it's based on a bunch of assumptions, and it's been worked out to be a mathematical certainty in its own modular way, but that doesn't correlate to reality. We know the model is based on a bunch of assumptions that had to be made in order to justify, for example, this transition from day to night. If you're going to put the sun at the center and have a heliocentric model with the Earth orbiting the sun, in that model, it can't be a level, flat Earth, can it? It would have to have some way of transitioning from day to night. And so that's how it's done. It's not measured. There's no measurement of the speed that Earth travels in either as in an orbit around the sun or as the spin on its axis. This has never been measured. It's not like you would measure the speed of a tire or a wheel of a car turning to show you on something on the odometer. That's not actually happening. There's no physical measurement of this taking place. It's just a calculation based on the length of a day and the size of the Earth and how long it would take to do a full rotation. All right? So, as Bruce says at the end here, food for thought, and I hope it is. And let's see what everyone has to say about this. Thank you very much.